Hi class, we are here for the last section of chapter 8, chapter 8.4, Matrix Exponential. Basically what we're going to do here is we are going to talk about what it means to raise e to the power of a matrix, right? So we can raise a matrix to a power, right? We can have, if we have a matrix A, and it's a square matrix, we can raise it to whatever power we want. Okay, that's good for linear algebra. That's not super helpful for what we need to do. It is at times, but it's not. What we're going to do now is we're going to talk about raising e to the power of a matrix times our variable component, right? So this is going to be very, very helpful for having us solve differential equations, systems of differential equations. It's a very powerful method. It allows us to basically use an approximation of with the Taylor series. Okay, so in order to relate this to things that we know already, okay, we know that the equation to a very, very standard differential equation, y prime equals some constant of proportionality times your original function, has a solution of y equals some constant times e to the kt. Right, we learned that way back in chapter 1. You learned this way back in calculus, even pre-calculus or algebra 2. Maybe not so much for the derivatives, however, but you know that this was an important style of function, right? Exponential growth and things like that. So, if we talk about the Maclaurin expansion, the Maclaurin expansion is the same thing as a Taylor expansion, except that a Taylor expansion, you can be centered at a value of x equals 2/3, for instance. The Maclaurin expansion is the Taylor expansion centered about the point x equals 0. It's generally much easier to compute. It has a little bit nicer properties, I guess you could say. So we're going to talk about that, right? So we know that if we take this centered about x equals 1 or t equals 1, and we do a Taylor expansion, that will give us our Maclaurin expansion, and that expansion is 1 plus k times t plus 1/2 k squared t squared all the way to 1 over m factorial k to the m t to the n. Okay, it's a very, very easy expansion to do. And again, if it was a Taylor expansion, we would have this would be t minus a, right? This would be t minus a squared, t minus a m, where a is that value that we are taking that expansion to be centered around, right? Here, we're centering around 0, so we don't have to have any of that crazy stuff inside of here. It's always much easier to deal with, okay? I can compute this sum in its indexed form with our series here, right? Our epsilon being from n equals 0 to infinity, okay? 1 over n factorial, k to the n to the n. So when we have x prime equals a times x, we have a generalized solution of a solution vector x being e to the at times my constant coefficient vector. Okay, and again, that's really just coming from this, right? X prime equals ax, y prime equals ky. Here, this a coefficient matrix is the same as this constant proportionality. Okay, so our solution with a coefficient, this c in front, being e to the kt, right? Ky, ax, that's the at here, right? So it's really just an analogy, it's an expansion from this idea from a single dE, okay? So here, we want to know, how do we expand e raised to the at, right? So it's very, very similar, in fact, how we did e to the kt, where k is a constant, okay? It's the same exact thing. Everywhere I see k, I'm replacing it with my matrix A instead. It's the exact same thing, same formula. Instead of k everywhere, I have a everywhere, right? If I want to take the derivative of this, which is important since my solution vector is x, and x prime would be the derivative of this, I would like to know what my derivative of this thing is, right? So the identity matrix goes away. Here, the t goes to 1. I'm left with just a. Here, the t squared turns to 2t times the 1/2 makes the 1/2 go away. So I have a squared t and so forth, okay, until I have this form. So I'm not going to write the generalized form, but the generalized form would be easy, right? This would be 1 over n minus 1 factorial, right? A to the n, t to the n minus 1, which is my generalized form that I have here. But instead of using the series notation, I'm just using the generalized form here, which is the same thing, right? So here, everything has a term of a, so I can factor out that common a term. That is going to leave me with I plus a times t plus 1/2 a squared t squared and so forth, which is the exact same thing as e to the at, right? This e to the at is what I get when I factor out the a after I take my derivative. So the derivative of e to the at is just a e to the at, which is what you get when you take the derivative of e to the kt, for instance. If I took this derivative, I would get k e to the kt, which is what I would have here, k e to the kt, which is y prime. So this satisfies the condition of being a solution, okay? So therefore, x prime equals a times x. That's a times my solution here, okay? Remember, constant, it's just a constant. When you take its derivative, it disappears, right? E to the at is a fundamental matrix, right? So it satisfies the condition that it would be a solution for the non-homogeneous case, okay? So we know the solution is the form of the generalized solution to the homogeneous equation and the particular vector solution to the forcing function, right? So the solution for the dE, for this dE, is the superposition of the two solutions, okay? So we can write this solution as e to the atc plus e to the at times integral from t naught to t e to the negative as times f of s ds. So we get the change of variable. This comes from that fundamental matrix that we're talking about in the last section. E to the at is a fundamental matrix. Before we were calling it phi, right? Phi times c plus phi times phi inverse f of t dt is what we had before. Here it's slightly different because it is e to the negative as. So if I have e to the negative 1, right, that would be the same thing, or inverse of e, right? That would be e to the negative as. So this is actually the inverse of this, okay? Here we are differentiating with respect to s because of the way that e works, right? So we're taking our initial value up until forever, basically, okay? This, again, so I pointed this out in the last video, right? But this is basically just the Laplace transform, okay? E to the negative as times a function with the change of variable, okay? So again, here, notice that our u of t, which we know is phi inverse of t f of t, okay, is replaced by e to the negative as, right, because that's an inverse, right? So this, from the last time, is now being replaced by the Laplace transform, okay? So from 0 to infinity. So generally, that's what we're going to actually do. We'll have this t naught as 0, and we will go to infinity, right? Okay. So when I take my equation and I take the Laplace of both sides, I can start to transform my situation, right? So we know that the Laplace transform of a derivative looks like this, right? And the Laplace transform of a times x will just get me, here we're considering a, we're treating it like a constant, and my little x gets transformed into a big X of s function, right? So x naught, I know, is the same thing as e to the at 0, so just 1 basically, or the identity matrix. And so I can start to move stuff around here, right? So I have AXS, I will subtract this on both sides, and e to the A0 is e times, basically, it's just is that expansion evaluated at 0, which just gets me the identity. Okay, so again, if I have this and I plug in t equals 0, everything goes away except for the identity matrix. Okay, so when I evaluate this, I don't get out 1. I'm in a matrix world. This is a matrix. I get out the negative identity. Okay, so I've moved this over to the right hand side. This AXS is still there. Of course, remember, this is just an algebra problem now. I'm trying to solve for x of s. So I can do the inverse Laplace and come back into the world of f. So I can pull that out as a common factor. And I have a minus s times the identity, because again, these are all going to be matrices. A is a matrix, is going to be equal to I, right? So I can change the sign here. And then if you notice, this is very similar to what we were doing before with determinants, right? Some multiple, constant multiple of the identity minus a times something else, right? Some vector. So if I want to solve for xs, I need to multiply on the left-hand side by si minus a inverse. So I do that times the identity. Anything times identity is exactly what you started with, right? 5 times 1 is just 5. So a matrix times the identity is just your matrix. So my transform of my homogeneous differential equation is just going to be this matrix, s times I minus a inverse. Okay. If I take the Laplace transform back, the inverse Laplace transform, I get e to the at is the inverse Laplace of the inverse of si minus a. Okay. So let's go ahead and do an example. So I want to solve x prime equals 1, 0, 0, 2 times x by using the matrix exponential. So I know I have this property that x is e to the at times this coefficient vector. So I need to start to do my e to the at. We do the Maclaurin expansion. I need a couple of powers of a. Luckily, this is a diagonal matrix. Taking powers of a diagonal matrix is extremely easy. You just raise the diagonal to the powers. Now, if I had values in either of these 0 positions, I would actually have to multiply my matrix out. I could not just say, oh, I'm just going to square each entry or cube each entry. That's not the way matrices work when you take their powers. That's only the way they work if your matrix is a diagonal matrix like the one we have. Obviously, this can go on forever unless we find a generalized term. So we can just write out a few terms, or we can find the generalized term and play with the generalized term instead. Sometimes that could be very difficult, however, depending on the matrix you have here for A. So for e to the at, we'll start with the identity matrix, plus t times a, okay, plus 1/2 times t squared, plus 4t squared, right? So I'm going to keep the coefficient on the outside, and then when we put it all together, we can start putting it together, right? So I have the first 4 terms, and we know it just continues in that fashion, right? So if I put these back to my matrix form, this is what it's going to look like, right? If I add all the terms up, the lower left corner is always 0, so it's always 0. The upper right corner is always 0. I always have 0. So on my main diagonal, I have a 1 plus a t plus a 1/2 t squared plus a 1/6 t cubed, and so forth and so forth. So again, if I had different entries here, I would have entries in this secondary diagonal here that would be completely different from what I have now, right? So even here you can see that these things are different. So this expansion, this is just e to the t, right? 1 plus t, that was a 1, right? Plus 1/2 times 1 t squared. So this is just e to the t. Here it's the same thing, but times 2, so that's e to the 2t if we compare this to the expansion for e to the kt, right? So e to the t, e to the 2t is my e to the at expansion, and that's my answer. I know x is e to the at times c. Well, I know what this fundamental matrix is now. It's e to the t, e to the 2t. So I have c1 times, this is 1, 0. This is 0, 1, right? There's nothing else there. E to the t. So if I pull that out as a constant times this first one, that gives me that vector. If I pull this out as a constant, that gives me the second vector, right? Very, very, very easy form of finding that solution for x. Okay. Now let's look at a non-homogeneous case. Okay, I have basically the same thing with a forcing function. So we already have our solution here, which is nice because I can just plug straight into this formula basically, right? I have my e a to the t c here plus my e to the at, and I need to find the integral from 0 to t of e to the negative s, e to the negative 2s. So all I'm doing here is putting a negative in front of all the entries of my e to the at. Very, very easy to do. And so when I multiply these out, right, I still have my first term here, my fundamental matrix, and then this is what I get when I multiply those together. So basically the 0 to t is just going to be a change of basis, right? Once I integrate it, I'll integrate it, but the 0 is not going to really do too much. I do have e to whatever, so I will have some 1s that pop up from this, but mostly it's just a change of basis going on here. Okay, so here is my homogeneous solution, that fundamental matrix, and then this is what I get when I integrate from 0 to t for my input here. Okay, so now I need to add these two together. I'm sorry, multiply these two together. Okay. Okay. And so I don't know if you can see this, but if I were to try to pull these apart a little bit, I have a single e to the t here, and I have an e to the 2t here, right? That's they're both kind of isolated. They can be thought of as multiples of these two vectors that are here already. So these two things they're not going to just disappear, but they're going to get kind of absorbed by the C1 and C2 constants here. Okay, so I still have my constants here. So as you can see, the ET is gone because it is able to be factored out because there's only one of them on top. There's no e to the t on bottom. So if I separated these things into vectors, I would have just an e to the t on top with none on bottom. That's a multiple of this one. Same thing with this e to the 2t. There's a multiple of that on the bottom, but there is no e to the 2t's on top. So if I separated these into, I guess it would be 6 vectors in this case, into separate vectors, the e to the t is on top and would be absorbed here. This 1/2 e to the 2t is the only one on the bottom. There's none on top. So that can be absorbed by this constant multiple of the 0, 1 e to the 2t vector. Okay, so it gets simplified into this form, right? And that would be our answer. Okay, so we got the homogeneous, and then this is the solution to the non-homogeneous portion. Okay, so one more example. We are going to do the same one that we did at the beginning, but instead of using the matrix exponential, we're going to use the Laplace transform. Okay, so we know e to the at is the inverse Laplace of si minus a to the inverse. Okay, so we'll start here. If I start with this, s times I minus my matrix A, that will give me s minus 1, s minus 2. Finding the inverse there is just 1 over the determinant and then me switching this position. Okay, the determinant is s minus 1 times s minus 2, right? 1 over s minus 1 times s minus 2. And so me switching these positions and multiplying that across, the s2 cancels in the first and the s1 cancels in the second. So it really just looks like I'm flipping these over. And in fact, I actually am, because it's an identity matrix. And remember what I said about powers of diagonal matrices, right? It's a diagonal matrix, so I can just raise each of the independent parts to the -1 and it'll flip over. So again, if I had entries in these zeros here that were non-zero, it would not look like this, right? So I have my inside of this inverse Laplace. I know what this looks like. So I need to bring it from the world of s, right, back into my world of t's. Okay, so I got to go from back into my equation basically. So this means that e to the at is the Laplace inverse of this, which is going to be the Laplace inverse of the relationship, right? These two things are equal. So that's going to give me e to the t and e to the 2t. Okay. Therefore, my solution is e to the at that I found using the Laplace transform times c1, c2. And again, if you remember, that is the solution I got by doing the matrix exponential. So using the matrix exponential and the Laplace transform will give me equivalent answers. So if you guys like the Laplace transform, you can use that in this section. If you guys would rather do the Maclaurin expansion, then you can do the expansions, right? That's it for chapter 8. I'll see you for chapter 9, where we discuss numerical methods, right? So we've discussed a few numerical methods already. We're going to go into a much deeper depth and detail about those in chapter 9.